control bacteria. So it may light up a little bit, okay, because it does have some ions in it. Strong electrolytes, weak electrolytes, non-electrolytes. Make sense? Questions? Page 2. Okay, so now we get to a concept called net ionic equations, okay? In lab, a week or two ago, you did a series of copper reactions, correct? Okay? One of the ones that you did is you took copper ions in solution, a nice blue solution, okay? Which is really copper sulfate is what it was, but these were copper ions in solution, okay? So I'll write it like that, okay? You took and threw in some zinc metal, okay? Finely divided pieces of zinc or little pieces of zinc that you cut up, okay? Do you remember what happened? Okay? It turned black, okay? Or a rusty brown. Basically what happened is you did a redox reaction. You changed this to zinc ions now in solution and you plated out metallic copper, okay? And depending on how finely it was plated, it might have turned black or it might have looked black. If it was a little bigger pieces, it might have looked more copper color. And so basically that's what you did in lab. You did a redox reaction. Well, basically what we want to find out, okay, is we want to understand what happens in a chemical reaction. We want to look at the net of what happens. So let's take a reaction and go through the different chemical equations and understand how we might describe the different chemical equations, okay? And we'll use this one kind of as a base. Let me get some room here. So if I take copper sulfate, okay, aqueous, okay, it's a nice blue solution, okay? If I take some zinc metal, elemental zinc metal, okay, it's a solid, and I allow them to react, okay? Anybody know what type of reaction this is going to be? Did you talk about reaction types? Okay, it's a metal displacement or a single displacement, okay? So it is a single replacement or a metal displacement. Sometimes people shove the words together and call it a single metal replacement, okay? And basically, this metal is going to replace this metal. And so what happens is you create zinc sulfate, okay, and you create copper metal. And that's pretty much what we just got through writing to lead into this, okay? Is that equation balanced as it's written, yes or no? Okay? Answer is yes. There's one copper on each side, there's a sulfate group on each side, zinc on each side, okay? Copper is positive 2 ions, sulfate's negative 2, zinc's usually positive 2, so it's balanced, it's ready to go, okay? This is the total balanced equation, okay? Kind of what we dealt with last week, okay? Learn how to write equations and so on and so forth, okay? Got to know the symbols and charges and formulas and all other good stuff. Make sense? Now, if we want to kind of understand what's going on, we need to write these equations in a little bit different format. So based on your solubility rules, based on what you know about strong acids and bases and solubilities, we're going to write this reaction a little differently, okay? So I'm going to write this copper sulfate instead of as a compound, I'm going to write it the way it breaks up, if it breaks up. And so we know it's aqueous, we know it's soluble, and so it breaks into copper positive 2 ions that are aqueous, correct? Plus a sulfate anion that is aqueous. So does everybody understand how I got from here to here? And so basically now, if I can, I am going to write each component of this in a simpler way, if possible, okay? Now the zinc is elemental here. Can't write it any different than elemental zinc, okay? So it's going to be written as elemental zinc, just like it is above. Help me write this compound in the same format, what would I write, please? Okay, so I'd write a zinc positive 2 cation that is aqueous, okay, plus what?
Sulfate.
Plus a sulfate ion that is aqueous. Very good. And then how would I write the copper elemental? Just copper elemental, same way, okay? So the second equation is called the total ionic equation. Okay, it shows all of the ions. If I had water in here, it wouldn't break up into HOH, it would break up into H2O because it's a molecular compound. If I had a strong acid, it would break up. If I had a weak acid, it would probably be together. Okay? But balanced equation is easy. Okay? The total ionic equation is understanding using your solubility rules, using what you know about strong acids and strong bases, okay, to write things in ionic form like I have here. Everybody with me? Now the last equation I'm going to write is something called the net ionic equation. Basically now what I'm looking for is things that undergo a change. Okay? Things that undergo a change, because if they don't undergo a change, we're not going to include them. Does the copper undergo a change from what you see on the left side of the reaction to what you see on the right side of the reaction? Yes. Okay? Now most people say, well, it's copper over there, it's copper over there. No, it's copper in an ion and it's copper in an elemental state. So it has undergone a change. Okay? So, to write the net ionic form, I'm going to say copper, aqueous, positive 2, AQ. And on this side, copper is solid. Not a very good arrow. Everybody with me? What about the next species, SO4 negative 2 ion? Is it undergone a change or not? It is SO4 negative 2 aqueous there. It's SO4 negative 2 aqueous here. It is not undergone a change. I am not going to include it in the net ionic equation. What about the zinc?
Yes.
The zinc is elemental on one side of the equation, and it's in ionic form on the other side of the equation, so it gets put into the net ionic equation. Is there anything else left to deal with? No, I've dealt with all the species. So you have, or can possibly have, 3 different types of equation. The balanced chemical equation, which you should be practicing on, okay? The total ionic equation, breaking these up into ions, okay? Understanding your strong acids, your weak acids, your strong bases, your soluble salts, okay? And then writing your net ionic equation. Anybody know what this guy might be called besides sulfate? Okay? Anybody watch the baseball game last night? Okay? Nobody watched the World Series game last night. Bunch of baseball fans. Okay, okay? Baseball game, the World Series going on, game 1, 14-inning game, longest game 1 in history. Okay? I fell asleep in the middle of inning 10. I couldn't take it anymore. Okay? How many guys play baseball on a team? But you really don't know baseball, do you? There's 9. There's 9 people on each team. So a total of like 18 guys, and then they had some subs. So maybe 25, 30 guys played. The stadium has 65,000 people in it. What are those 65,000 people called? Spectators. They're watching it. They're not part of the game. These are called spectator ions. They do have to be there to make things happen, but they don't change. Okay? So in a set of ionic reactions, the ions that don't undergo a change are called spectator ions. Okay? Those 65,000 people at that ball game screaming, cussing, yelling, drinking, whatever, okay, didn't really affect that game. It's the players that affected that game. These are the players. these are the spectators. Make sense? No more baseball analogies. It doesn't work very well. All right, so there are several examples, okay? Make sure I got all these things. Remember, if it's a soluble salt, it breaks down. Strong electrolytes. Spectator ions. Okay, so I think we got all of his what he wanted to do. So let's 1, 2, 3, 4, 5. He's got 5 examples there. Let's do a couple, 3 of them. What, 4:30? Is that what time it ends?
4:25.
4:25. Close enough. Okay. So let's do a couple of examples and see if we understand this concept of equations here. All right, so the first one is calcium hydroxide, okay? And it says it's aqueous. Of course, you know, hopefully from our conversation of just a couple minutes ago, that it's a group 2 base, so it's a strong base. Magnesium bromide. It also says it's aqueous. It is a soluble salt, okay? Yields magnesium hydroxide. So here they're writing it as a solid. It is a group 2 base, but it's one of the lighter ones, so it is weak. So they're writing it as a solid. And then calcium bromide. And they're writing that as aqueous. So even the states of matter give you a little bit of insight of what might be happening here. But again, you got to use those knowledge of strong acids and strong bases and soluble salts and then other things. So here is my balanced chemical equation. Well, it's a chemical equation. I don't know if it's balanced yet. Okay? But here's my chemical equation. The very first thing you got to do with any chemical equation is to balance. Is it balanced? Yes or no? Okay, appears to be balanced. I see 1 calcium on each side. I see 2 OH groups on each side, magnesium on each side. So pretty easy one to start with. It is balanced as it's written. Okay, so this is the balanced equation. You do need to know how to write the balanced equation as we have done here. Now I want to write the total ionic equation. All right, so help me out. How would I write that? Well, the calcium hydroxide is aqueous, it's soluble, it dissociates. So, help me write it. What would I write? So the calcium ion is positive 2, it's aqueous, okay? And now what? Okay, it's a hydroxide ion, it's negatively charged, it is soluble, but there are 2 of them. Okay? Now, why did we have the 2 here for this equation, but put the 2 here for this equation?
Because you can't put it on the other side.
Okay, because this is in case of parentheses, because it's polyatomic, used more than once, but really there are 2 amounts of it, okay? There are 2 units of it. And that's really what it's telling you here. There's 2 units of that, right? So make sure you understand how I got from one nomenclature to the other. All right, so that is now represented correctly. Yes? Continuing on. Okay, the MgBr2 is an aqueous compound, so what would I write? Magnesium ion is positive 2, it's aqueous, and then what? Okay, the Br ion, it is also aqueous. Missing something. Coefficient of a 2 in front of it because it's used twice there. Everybody good? All right, as we continue on, now we get to the magnesium hydroxide. It is a solid, meaning it's insoluble. It doesn't break down into ions. So how would I write it for this equation? Exactly the same way. Okay? Doesn't break down, and so write it not broken down. It is a solid. Okay? It does not dissociate. So write it just like it is. So remember, if it's a soluble salt, it breaks down. If it's an insoluble salt like that, it's a solid. It doesn't break down. All right, and then the calcium bromide, how would I write that?
And how do you know if it's soluble or non-soluble?
Say again, please.
How do you know if it's soluble or non-soluble?
Okay, so first of all, it said it in this problem. Okay? So it said it in the problem, but if you didn't have the problem, the solubility rules,
Oh, that's
okay, would help you to understand, okay? And remember,
chart.
yes, okay? And then it's a group 2 hydroxide. All the group 2 hydroxides, the heavy ones, calcium and below, are soluble. That means magnesium is not, okay? Magnesium hydroxide is what you actually take. If you ever taken milk of magnesia, read the label. It has magnesium hydroxide in it, okay? Some of you are going, God, I hate this stuff. Okay. Did I answer your question okay?
Yes.
Very good. Everybody okay with the calcium ion written like so? And then finish it up. What do I got to do with the bromine? 2 Br -1 ions that are aqueous. So that should be my total ionic. Next is my net ionic. And so now all I'm doing is trying to search out what has changed. Help me out, please. Calcium ion.
It's the same.
It's the same here, and it's the same here. It is called a what ion? Spectator. Okay, it's just cheering, but it's not participating. Okay? The hydroxide ion in this side, and something that contains hydroxide in the other side. Any difference? Yeah. Right? So here I got 2 OH ions in solution. Okay? And on the other side of the arrow, I've got this compound MgOH2, which is a solid. Which should key you off to saying that the Mg is probably going to undergo a change. Okay, so we've got this taken care of. If you want to put a little check mark by it to make sure that you've done it, okay, or underline it, whatever. So I've got to put the Mg here, +2, aqueous. I've done that. I've taken care of that. What's left?
Nothing that changed.
Nothing that changes, but you do have to account for bromine spectators, okay? And so this is your net ionic equation. That's what's making this reaction do its thing. Okay? Even though you got to have the calcium or some other ion that creates a soluble salt. So what's the purpose of this is, if I was a practicing chemist, and that's my day job, okay? I'm a practicing chemist. If I don't have any calcium hydroxide, well, maybe I got some strontium hydroxide. And the calcium is a spectator. The strontium is likely going to be a spectator. I could probably substitute strontium oxide and make this reaction work. Because all it does is spectate anyway. But I got to have something to pull off the shelf and mix up in the water. Okay? So it does need to be there. Okay? Here this is bromide. Maybe I don't have any magnesium bromide. But maybe I got some magnesium chloride. Okay? And if it's soluble, then it'll work. If I want to make that magnesium hydroxide, basically I need a source of hydroxide ions. I need a source of magnesium ions. So if I could get some hydroxide from strontium hydroxide, if I could get some magnesium from magnesium chloride, I would still have the same net reaction at the end of the day. Who cares what else I mix it with? Because this is all I want to get. So that's why we do this, okay? To show you that you don't necessarily need to have calcium hydroxide to make this reaction work. I could use strontium hydroxide. I don't need magnesium bromide. I could use magnesium chloride. And I could get the same end results. Make sense? Let's look at another one. How about the third one? Let's do the third one. CO2 gas. So it's telling you that it's CO2, and it's telling you it's a gas, okay? So gases are written in that form, so don't break them up, okay? H2O liquid, okay? I really impressed that person in lab. Okay. Calcium chloride, aqueous. And then 2HCl, aqueous. And then there is another one here, calcium carbonate, solid. Okay, so there is the equation. Okay, yeah, it actually balanced it for you to begin with. Okay, yes ma'am.
I think the arrow's supposed to go after the
Exactly the
C.
same.
Yep, you're right. Thank you very much. Thank you. Okay? So, there's our equation. Is it balanced? Verify that it is balanced. Verify that it is balanced. Okay? Got some people shaking their head yes, and I got this guy saying no. Tell me how it is not balanced, sir. Never mind. Okay. Is it balanced? I believe it is. Okay? So that's the total balanced equation. Okay? And because of the way it's written, he gives you some hints. Okay? Or because you can use your solubility rules, that's a gas, and he has to tell you it's a gas. That one you know is a molecular compound. It is a liquid. Okay? It does not break into ions. CaCl2 is aqueous. It's a soluble salt. Most all the chlorides are soluble salt. There are a couple of exceptions. Okay? HCl, AQ, hydrochloric acid in water, solution, strong acid, soluble. And then CaCO3, most of the carbonates are insoluble. Most carbonate compounds are insoluble. That's on your solubility rules. All right, so now we're ready to write the total ionic. So, help me out. CO2 gas going to change? Nope, it's a gas. Not going to change, okay? CO2, it's going to be gas. It's going to stay that way. It's not, doesn't dissociate, okay? Excuse me. Is the water going to disassociate or change in any way? It's a molecular compound. No, it's not. H2O. Now, what about the aqueous salt calcium chloride? Yeah, it's going to break down into calcium positive 2 ions and 2 chloride negative 1 ions, like so. Because it's a soluble salt, AQ. You can look at your solubility rules, it'll tell you it's soluble. Any questions on the left side of the equation? Right side of the equation, hydrochloric acid, strong acid or not? HCl, is it strong acid? It's one of the strong acids. So it's going to produce hydrogen ions in solution and chloride ions in solution. And of course there's going to be 2 of these and 2 of these. And then the last species here, which I'm going to run out of room because they wrote too big, CaCO3, it's a solid, it doesn't break down, it's insoluble, so you write it as a solid. Questions about the total ionic equation? And so now we got the net ionic equation. So, what's going to happen here? Do I need the CO2 gas? Is it over there as CO2 gas? No, so it's part of the net, okay? So, CO2 gas. Water occurs on the left. Does it occur on the right? No, so it's part of the net. What about the calcium ion? It's calcium ion over here. What's its form over yonder? It's part of the compound, so it's part of the net ionic. Okay? What about the chloride ion?
It doesn't change.
It doesn't change. It's a spectator. Okay? I have gone through all the items on the left side of the equation, correct? Now I'm ready to go to the right side of the equation. Did the hydrogen ion, is it changed? Is it different? Wasn't hydrogen over here, right? So it needs to be part of this. And then what's left? What's the only thing that's left? The calcium carbonate. So this one uses most of the species in the net ionic. Okay, the only thing that is a spectator is a chloride ion. Which should go to tell you if I could find something else that's soluble. I could have used, instead of hydrochloric acid, okay, HCl over there, I could have maybe, or CaCl2, I could have maybe used calcium bromide or calcium fluoride, something else that was soluble, because it's going to be soluble over there. Okay, so that's what it's telling you. Okay, now maybe that's a little more advanced from where we are right now, but that's how a practicing chemist would use a net ionic equation in the laboratory. And believe me, over the years I've done this, okay, in the laboratory, I hadn't had something, I could swipe something else and come up with the same net effect that I would like a student to see, or in the lab I like to see. Make sense? Let's do one more, and then I'll give you the opportunity to do the couple others. Let's do the last one. Okay? Let's do the last one. So you work on it for a couple minutes, and then we'll look at it as a whole here. Personally, I think this one has a little bit of issue the way it's written. Okay? Let's look at this one together. H2SO4 aqueous, we know that it's sulfuric acid is a strong acid, we know it's aqueous. Sodium fluoride, again, most of the group 1 and the halides are soluble salts, so I agree with that being aqueous. Sodium sulfate, again, a lot of sulfates are insoluble, but sodium sulfate, group 1 sulfates are soluble. I have a little bit of a disagreement with the HF, okay? Based on what we said earlier, okay, HF is not strong acid, okay? HF is a weak acid. I think HF should be not AQ, okay? Again, I'm not going to go against what Dr. Burns said, but I might have a little bit of issue with this one. And again, chemists like doctors, we all have our own opinion about things, okay? So we can look at it that way. We might look at it a different way. All right? Everybody good so far? Is it balanced the way it's written? Should be, hopefully. All right, so let's write the total ionic. So it should be 2 hydrogen ions, AQ, plus the SO4 -2 ion, AQ. Everybody good so far? Okay. And then if I follow along, I got 2 sodium ions in the solution and 2 fluoride ions in solution. Looks good so far. All right, then if I continue on, I get 2 sodium ions in solution, and then an SO4 -2 ion in solution. And then, depending on how I write this, okay? If I write it the way Dr. Burns has it written, I would write 2 hydrogen ions in solution, and, because I write too big, okay, 2 fluoride ions in solution. That's the way Dr. Burns has got it written, okay? I might write it as 2HF, okay? Because I think it's a weak acid, and so I would not make it an ionizable, okay? So there may be a little difference there, okay? With me? Everybody okay with the total ionic equation, whether I do it in this format, the way Dr. Burns had it, or if I do this slight modification because I'm calling it weak. All right, so now we're ready to do the net ionic. So here's the first thing you get to could be different because I got 2H positive over there. If I write it Dr. Burns' way, it's a spectator. If I write it my way, then it's involved in the reaction. Okay? So let's leave it for a second. Here, this is the same here, and this is the same here, so that's spectators for sure, right? What about the sodium ion? It's spectators because it's exactly the same here and here. Now, here's where I would now have my argument for my case, okay? In a reaction, we're trying to make something change. If I left it in Dr. Burns' format, what's the sense of doing this reaction? Nothing's changing, right? There's no purpose to this reaction, right? I'm just throwing chemicals together and I can't distinguish them, okay? But if I take my course of action, then sure, I take hydrogen ion